Okay, so the water potential equation, psi sub W is equal to psi sub P plus psi sub F. All right, so let's see. Last time we did go over the idea that you're thinking about hydrostatic pressure for the psi sub P. And then for the psi sub S, that's representing the idea that there's, if you don't have pure water, if you have some kind of solutes in there, you automatically start developing an osmotic potential. So when you think about osmotic potential, this value is actually a negative number. So really, even though they say psi sub W is equal to psi sub P plus psi sub S, just realize that the psi sub S value is going to be a negative number. And the reason for that basically is that anytime you dissolve solutes into water, you're essentially decreasing the free energy of that water. And so it drives your psi sub F into a negative scale, a negative number. So pure water has a psi sub F of 0. But then even just one molecule of glucose, and you started thinking about a negative number. And remember the mantra from last time, more solute, more negative psi sub F. The more sugar you put in there, whatever, it's going to drive your psi sub F into a more negative value. Psi sub P, if you think about what we've been talking about so far, we're thinking about like an intact plant cell. You could have a flaccid cell, and that could be a psi sub P of 0. When we say flaccid, we mean there's no hydrostatic pressure being exerted on the cell membrane or cell wall. Or if we have water rushing into that cell, it's going to be some positive number. So your psi sub P, for what we're talking about right now, can be either 0 if it's flaccid, or some positive number if there's pressure being exerted on the cell membrane or the cell wall. All right, so that's how we think about that equation. And then we started looking at some ideas, kind of like thought processes of what happens if you have a plant cell, so that has a selectively permeable membrane. And then we're thinking about if you drop that cell into a beaker of water, what is going to happen based on the laws of osmosis. So let me shift into this other. Let's see if I can reshare. Okay. So we're doing, do you have a piece of paper that you can rip out, and we're going through this as participation points? So just make sure your name's on it, because I'll be collecting this in a minute. So I just want you to think through this. And so we have this scenario where we have a beaker of water, and it has a water potential of negative 0.15 Pascal. The cell, someone did that calculation, it's negative 0.25. And so we need to think about this negative scale. The beaker has some solutes in it. The cell certainly, if it's living, it definitely has some solutes in it. So then we think about this idea of, osmosis is a two-part definition, right? Plant cell, negative, your beaker. The laws of osmosis, or the definition of osmosis, is movement of water across a selectively permeable membrane. All right, so my computer is possessed when it comes to hooking into projectors in this building. Works fine in the other building. All right, so which way will water move? Thinking about the scenario that I put on the board there, A, B, or C. How is water going to move based on water potential and the laws of osmosis? So we say water will move from less negative to more negative when we think about water potential. Got that one? Okay, next question. What now happens to the psi sub s portion, that component of the cell? So you drop that cell in, water starts moving. What's going to start happening to the psi sub s of the cell? Are we ready? Okay. What about the psi sub p of the cell? What's happening to that? All right, so now let's flip and start thinking about what's happening in the beaker. So after you start this experiment, what's happening to the psi sub s component of the beaker? Okay, what about the psi sub s of the beaker? All right, that's the end of those questions. If you want to take a picture of your answers, you can, but mark those. How did you commit to answers today? And nudge you to thinking about this? I'm not going to break you. Okay, so water potential, thinking about moving of water, think about water, think about the idea that water is going to move from less negative to more negative water potential. And based on that, and what we have drawn here, so which way will water move? Into the cell or into the beaker? Into the cell. Why? Yep, the cell's more negative, right? 0.15 is closer to 0 compared to 0.25. So less negative in the beaker, more negative in the cell. So water will move into the cell. So from the beaker into the cell. Okay. So if you have that happening, what's happening to your side sub S of the cell? So water starting to go in, and assume like a big movement of water, lots of water's going into the cell. So what happens to your side sub S under those conditions? Water rushing into here. What does that do to the solutes? Does it make the solutes more concentrated, less concentrated? Less concentrated. So then what would happen to your side sub F? What do you think? If it's becoming more diluted out, less concentrated, what would that do to your psi sub S value? You know already that the cell has negative psi sub S. There's some negative number, but now you start having water rush in. What's going to happen to your psi sub S? It'll become less negative. Oh. So you're diluting out the solutes of that cell. You can think of it that way. And that will start get your psi sub S value closer. It won't be 0, but it'll get closer. What about the size of P of the cell? There's a lot of water rushes in. What's happening? It increases. It's an intact cell. So there's a definite enclosed cell membrane, cell wall. So as you have water rushing into that, it's going to start to create hydrostatic pressure. So your size of P is going to increase. It's going to become positive. All right, now we need to switch and think about the beaker. What's happening in the beaker? So you have water exiting out of the beaker, going into the cell. So what does that do to your psi sub S component? Water's leaving, the sugar is staying behind. Yep, it's going to drive your psi sub S more negative in the beaker. You're concentrating that sucrose solution. And so when you take it as a total, you're making it more concentrated with your sugar solution. That's going to make your psi sub S value more negative. What about your psi sub P of the beaker? So this one you have to think a little bit about the idea of a membrane. Is there a membrane over the beaker? It's open to air, so it's open to atmospheric pressure. So plant physiologists say, we're going to say the psi sub P is 0 at atmospheric pressure. So your psi sub P is 0 all the way through this whole experiment in the beaker. Well, what do you think? How'd you do? Still feeling shaky on this? Yes? No? Eh? One thing that when I was learning this that helped me that was thinking about the mole. If you learn about mole fraction solution, mole fraction, which in this case you're thinking about the idea of water. So you would express it as moles of solvent, over right by moles of solvent plus moles of mole fraction divided by the moles plus your moles. And so if you start thinking about that ratio, that fraction, start thinking about how water is leaving a system or entering a system, that might help you understand a little bit more about, that as water is leaving, that's increasing your sucrose concentration in the beaker, that's going to drive your signs of acid negative. So if that helps, you don't have to spit that back to me. I'm not asking you to memorize that. Just saying, if that helps you think about this, then sure, go ahead and use that. That helped me. But I can post these with the answers provided, so you can use this for studying. The reason I'm spending time with you here to work through it and get thinking is that this concept now is really not going away in this class. You'll be hearing about water potential for the rest of the semester. And so if this is still something that is not quite there for you yet, this is my heads up to you. Please look through this and really start thinking about it, because it's going to be on the first exam. It's going to be on the lab quiz. You have to write a lab report about it. It'll keep showing up in subsequent topics as we work through the semester. And I remember when I first learned it, I had to sit down and really think through this. And so don't wait, because it's not going away, okay? Any lingering questions right now on what we just did or water potential in general? Stop share and get into, let's see. So I want to get into the next slide set on transpiration, which should be posted. We're still thinking about water, but now we're going to get into the idea of if you have a plant living its life, it has to acquire, get access to water and bring it into the plant body, and then get it coursing through the plant body and get it to where it's needed. And then actually a lot of it goes right through, all the way through the body and out through the stomata of the leaves. And so that whole process has been something that plant physiologists are very interested in, because it is so critical for plant growth and to get healthy plants. So we're going to dive down into the soil and think about what's happening there. root systems are incredibly important, of course, for water access. And it's actually the root hairs are the most work of the root system in terms of it's got great surface area for absorbing water. And so that's why if you've ever watched a YouTube video or something on how to repot your house plants, they'll always say make sure you water your plants very well and keep the soil nicely moist for several days. The reason they're telling you that is no matter how gentle you are when you're repotting, you do rip off a lot of the root hairs. And so now you've really hampered the plant's ability to efficiently take up water. So root hairs are really well designed for water absorption. Here they're trying to show some soil particles, the blue water, air spaces in the soil system. So we need to think about all of that. And I won't go into huge detail about soil. If you take a soils class, you'll realize it's very complex, lots of different types of soil out there. And here I just want you to think a little bit about the particles, what kind of sizes we're thinking about. So with coarse sand, of course, you have pretty big sand particles. And then you see on this, you can have different kinds of sand particles. And then as you get into silt and clay, you get much smaller particle sizes. But you can see that it has a big impact on your surface area of that particle. So coarse sand, fine sand, not the greatest surface area, but then you can see with silt and clay, you have great surface area. So maybe you might think, well, then why don't we just have soil that's all full of silt and clay? That's surface area. That's good, right? Well, of course, the roots have to be able to grow through that, and silt and clay packed together so nicely that it can almost become like cement when it dries out. So you have to have a mixture of different soil particle sizes in the soil system for good root growth. So as they're trying to figure out, okay, how is the plant taking up water into the roots? How is that happening? What forces are necessary to get that to happen? They started taking measurements and collecting some data. And when they looked at the water in the soil, they were measuring that the psi sub S value of the soil system pretty much, they took a lot of different samples of different soil systems, and they said it's around negative 0.02 megapascals, which is close to zero. It's pretty dilute. So they said, let's just kind of ignore psi sub S. It's so close to zero, which I'm fine with that. It makes it simpler. So they said, mainly when you look at the soil water, it's mainly a function of psi sub P that we need to think about in terms of how to figure out how the water is it moving toward the plant, away from the plant, what's going on. Now, in the soil, when you look at the water, and they started taking psi sub P measurements, figuring that out, they kept coming up with the idea that it's either zero, no pressure, or negative. So less than or equal to zero. So it's either a zero or some negative number. And again, that gets back to the idea that I briefly mentioned the other day, that if you think about negative pressure, that's the definition of tension. Tension is negative pressure. So that is saying that when you look at the soil water, that water is actually under a tension force when you have plants there doing their thing. And so now the question is, okay, why is there a tension force there? What's going on there? How is that happening? And then how will that help explain how the water is getting to the plant and then taken up by the plant? So going back to this idea of get water in the syringe and cap it off, and then you start pulling back on the plunger, you're putting a negative pressure on that water pump, putting a tension on that. And so they're trying to think, obviously you don't have syringes in the soil water creating some kind of weird tension. So they're like, how does this happen naturally? So what they started realizing, down here is a picture of some soil particles, and you can see the blue water there. And so figure A, you have really well watered, lots of pretty much saturated. And then figure B and C, you see more and more air spaces. which means, water is leaving the soil system. Well, remember that when you think about a body of water, it does have a high surface tension. We talked about that on day one. Okay, well, let's start thinking about it. So you have a well-watered soil. You have some roots in there. The roots are taking up some water. As that's happening, you start, of course, to have the water exiting the soil, going into the plant. And so gradually you'll have less water in the soil system, and you'll have more air spaces developing. So the water, when you look at a soil system, they're trying to show here in figure A by these white spaces that water is easy to pull away and get drawn up by the roots if it's like in the bulk water area and not the water attached to the soil. Okay. So just the bulk water in there in the soil system, that's pretty easy for the roots to pick up. So the water's first removed from the middle of the pores spaces. Okay, that's what they're trying to show in figure A. Then, because water, you do have these adhesion forces to think about, whether it's soil particles or the xylem inside the plant, water will cling to the soil particles, to the surface of the soil particles. And that's pretty much figure C is getting at that discussed it visually, where they're showing that you still have plenty of water clinging to the soil particles, even though most of the water in the bulk soil has been drawn up by the roots. Okay, so if that's happening, and you have the water in the soil system receding into smaller and smaller spaces as the root keeps taking up water, well, when you do that, you can see the artist has drawn here that you have these curvatures in between the soil particles. Okay, so they're trying to show there's these curved menisci that will develop with that water clinging and then receding into tighter and tighter spaces in the soil. The curvature of the menisci will start to get smaller and smaller and smaller and smaller. When that happens, it starts to develop a tension force on the water. So it's really getting at this idea that because water has such a high surface tension, and then when you wrap into the idea that you get the curved menisci in between the soil particles, and then that curvature gets smaller and smaller and smaller, you start to get a bigger tension. Now, the way to think about this mathematically is this equation. Psi sub p is equal to negative 2 times 2 divided by r. And if you play around with that equation, I think it explains a lot of what we just described on the previous slide. T is your surface tension, which is a known value, 7.28 times 10 to the minus 8th megapascals. And then R is your radius of the curvature of the meniscus. So that's what often chemistry lab or biology lab, they'll say, measure 20 milliliters into the graduated cylinder. Make sure to be accurate. Base of the meniscus, get it accurate. Looks like that one is not quite 20, it's over 20. But anyways, I think you're most familiar with that idea. You have to measure out something into a graduated cylinder. You look at the meniscus for accuracy. So what we're thinking about here is this idea that here in figure A, the curvature of the meniscus is pretty broad. And then figure B, you see it's getting smaller. So figure C, that's the smallest example. So the radius of the curvature of the menisci in figure C is very small compared to figure A. So A, you're seeing on that box up top, they're showing the curvature, the radius of the curvature in figure A is 0.5, in B it's 0.05, and then in C it's 0.01. So you're getting smaller and smaller radii as you go from A to C. And then if you plug that into this equation, if you put a small number in the denominator, that makes your overall value, you know, a pretty big number. But in this case, it's going to be a pretty big negative number. All right, so when you plug in 0.01 into that equation, you get a size of P of -15. If you do a number closer to 0, like, you know, 0.5, you get a modest size of P. It's only -0.3. So this is a way to describe what's happening in the soil system, because that R value, you're looking at all of those soil particles, you know, stuck together, hanging out with each other. You get these nooks and crannies in between the soil particles. And as the water is clinging to the soil particles with adhesion forces, you start to get those curvatures. And that really does generate a pretty decent tension. And as long as those water molecules are all, you know, cohesive with each other all the way to the root, you will get water movement from the bulk soil to the root by a tension force. So where did that go? I'll go back to this. Does that kind of make sense? All right, so the pet physiologists are saying you really don't need to think about size of S. You're really just thinking about size of P values as you're, you know, working through this. So that goes back to the idea of, if you're thinking about pressure and you can kind of ignore the size of S, which of those equations that we talked about, Fick's first law of diffusion or the Poisson bulk flow, which one is thinking about pressure gradient? Remember? Bulk flow or diffusion? Which one has a pressure gradient portion to the equation? Bulk flow. All right, so bulk flow, the Poisson equation, delta P over delta X. So you're thinking about a pressure gradient. So that's where they started looking. They're like, it looks like we got a pressure gradient, except technically it's a tension gradient. It's a negative pressure. And so what they're, you know, what they were able to measure is that when you look at the water right near the roots, those water molecules are under pretty good tension. The roots are taking up that water. The soil water is getting depleted around the roots. You get the really small radii of the menisci. And so you get a pretty good tension right around the roots of the water right there in the soil system. So that will make your size of P pretty negative. And then you get a pressure or tension gradient. In the soil. So you get pretty negative tension right near the roots, but further away from the roots, the water further away in the soil is under a low, you know, not as great of a tension force. And so you get a tension gradient. Pretty negative at the roots, a little less negative further out in the bulk soil. And so if you have a gradient like that, that means you can have movement. You're going to have water moving because of that gradient. And so basically that's what they see. Here's your little plant with its roots in the soil. And as if the roots are actively taking up water, definitely will get higher tension forces. So that means your size of P is going to get more negative at the root area right there, the water there. And then in the bulk soil away from the roots, your size of P is less negative. So you have, in this case, that's going to allow for your size of W less negative, more negative, which means the water is going to move from the bulk soil toward the root. And so that's essentially what the roots are doing all day long. As long as there's adequate water in the soil, they, by their activity of taking up water, they're allowing for this tension gradient to build. And so your size of P is more negative at the roots, less negative further out. And as long as you maintain a gradient like that, you'll have movement. You'll get water moving toward the roots, which is exactly what the plant wants. All right, so as they started studying the soil system and realized there's definitely some tension forces, negative pressure, when you have roots in the soil like that, plants doing its thing. And so they were able to pretty nicely put that together and say, okay, yeah, as the roots are taking up water, you get this tension force generated. You're going to have water moving from less negative to more negative size of P. Okay. So now let's imagine the roots are taking up that water. Now remember, vascular tissue, all that water has to get to the vascular tissue. To the xylem or phloem? Which one? Where is water going to get dumped? To the xylem or the phloem? Xylem, yeah. All right, so it's got to get there. And so they were, okay, how's that going to happen? And they came up with 3 hypotheses of how this could happen. And so they said, well, once water gets in, the root hairs take it up and it gets into the tissue of the root, it could just skirt around in the cell wall areas, flow through that way. If that's the case, they gave it the name apoplast. So they said it's apoplast movement. Or they said, well, maybe water dumps into the root cells and goes through the root cell and then goes out the other side of the root cell, gets into the next root cell. That sounds really complicated, but that's another way that it could be. It's called transmembrane, crossing the cell membranes all the way down, all along. And then the third idea is what they termed symplast, which means water gets dumped into like the first root cell. And then after that, it goes through the plasmodesmata tunnel system from cell to cell to cell through the plasmodesmata tunnel. And so those are theoretically 3 different ways. And so they were trying to figure out how this is happening. And of course, they're basing it on data on how quickly water is moving through the plant body. And if you think about it, that transmembrane method, having to go into a cell and then go out through the cell membrane and then into the cell membrane and crossing cell membranes all the time, that's slowing it down. And so they kind of pretty much said, yeah, transmembrane, not really a major factor here. So they don't even have that drawn on here so well. Well, I guess the blue is trying to depict the transmembrane idea. Then the symplast idea is the black line on here, where it's showing once it gets into a cell, it just goes through the tunnel system. And that's a little more efficient than transmembrane. And then apoplast, they show in the green here, where the root hairs get up, and then it's just skirting all the cells in the root tissue until it gets to the vascular tissue. And when they started comparing, thinking about these and then looking at the actual data, they were saying, it's probably the apoplast. It's probably apoplastic that's most efficient, and that corresponds the best to our data of how quickly things are moving through the plant, the water's moving through the plant body. So they have hypothesized that apoplast is probably the main mechanism. But here you see with the drawing, you have an interesting issue here. Once you get to the cluster of vascular, they've drawn like this cluster of vascular, you can see that there's this ring of cells called the endodermis, which I'd like you to know, please, that word. So the endodermis is that ring of cells. And you can see that red stripe through each cell. That's in the cell wall area. You can imagine like a box that you put a rubber band around, and think about the rubber band as this so-called Casparian. So the Casparian strip is just a beefed up ribbon of wax, essentially, that's laid down in the cell wall area. And what it does, I won't go into all the physics of it, but basically what it allows to happen is that water will only come in from the root hairs across all the cells here and get dumped into the vascular tissue, into the xylem, and won't flow back out. So it keeps moving the water in the direction of dumping it into the xylem and not having it come back out of any of these cells, back out into the main root tissue. You don't want that. You kind of want one-way flow. Just get the water into the xylem, and then once it's in the xylem, it can start coursing through the plant body. And so that Casparian strip really does force that situation. And so it's a simple design, but it very nicely makes kind of a one-way transport. Water is only going to go from the root hair into the xylem and not reverse out. So they were able to do this experiment, with measurements and looking at things, but then, saying, okay, well, let's say that it is the Eco-Plast movement, getting water into the xylem. Remember, in this case, they've drawn a dipole root. So you see this kind of cross shape, that's where all the xylem is, the tracheids and vessels. So they're like, okay, so the water gets in there, then what? How does it start moving through all those connected tracheids and vessels all the way up through the stem, branches, ultimately to the leaves? How is that happening? Well, the first proposal was maybe it gets pushed up the plant through the xylem. Maybe there's a pressure force that's kind of like pushing it up. And the reason they thought of that initially was they know that this is a strawberry plant. They know that, if you go picking strawberries or if you walk across your lawn early in the morning after a cool, humid night, but there was no rain and your shoes still get wet, and you're like, but there was no rain. Why are my shoes getting wet? A lot of it has to do with ductation. Fancy word, but basically you can show that water does get moved out of the grass, the leaves, or the strawberry leaves due to positive pressure, pushing that until they kind of ooze out of these special glands. And so that's kind of what they were thinking about. So the fancy word kind of ductation up here in the title. And so under the right conditions, usually you have to have a cool, humid night. The next morning, your shoes are going to get wet, even if it hasn't rained, as you walk across that low grasses. But so very pretty picture here showing the ductation. And that's due to positive pressure and causing the water to kind of ooze out of these hydrophones. Okay, but then they can't show that this happens in taller plants. Strawberry plants, if you've ever gone strawberry picking, I had to do that a lot when I was a kid, and I really didn't like it because you have to bend way down and hunt for the strawberries low to the ground, and it gets tiring. So these are small plants. Strawberries are small. Your lawn grass is small. So it can work for those. Ductation is a thing, but bigger plants, you don't see that. And so quickly they had to abandon this idea and say, yeah, that's probably not the way it's working. They also had to figure in the actual, what are we dealing here with? We're dealing with tracheids and vessels, and what are they composed of? They're dead cells, so that's good. There's no cytoplasm there. They didn't have to worry about that, calculate all that issue with liquid in there. But they had to look at the diameter of these, think about water flow through such a small diameter, and trying to figure out, could you push water through taller plants? And they figured out, no, it's just the physics wouldn't hold. It doesn't work. And so they really just had to abandon the positive pushing of water up through the plant body. So when they did more refined measurements and did all the math, they're like, yeah, it can't work through a positive pressure pushing up. So then they came around, kind of did a 180, and they said, well, if positive pressure pushing up through the tracheids and vessels it just defies the laws of physics, it wouldn't work. What about just the opposite? What if we think about tension forces, pulling the water up the plant instead of pushing it? And then they started running with that idea, and they started looking at this cohesion tension theory. So they call it the cohesion tension because water can be very cohesive in the sense that water molecules love to hang out with each other. They cohere to each other. Tension, they started thinking about a tension force being applied to that water in the xylem. And so the cohesion tension theory. And they actually started thinking about, instead of water being pushed up the plant, what if it's actually the forces at the top of the plant in the leaves causing a kind of a pulling or a sucking action on the column of water in the xylem. And so they kind of did a 180 on this idea of, let's think about water being pulled up the plant. And so here you have a leaf in cross section, and they're looking at the stomata are on the bottom here. And they knew that when you have water coming out of the stomata, it's in the gaseous state. So as the water comes out of the vascular tissue, out of the xylem there, so the red area, okay. So you have to imagine water flowing through the xylem, and then it starts oozing out of the xylem into the internal area of the leaf. So these water molecules come out. Remember, they're very cohesive, so they stick together. They start to coat the spongy mesophyll cells, cling to the mud, so there is some cohesion there too, because the water molecules, liquid water, they start to coat and cling to the spongy mesophyll cells. And then you have all this airspace. So you have liquid water with air right there. So you have an air-liquid interface. So now you have to start thinking about surface tension, right? Surface tension starts to come into play. Start to see liquid molecules clinging to the spongy mesophyll cell, and then some will evaporate, shift into gaseous phase, and go out. And then that keeps happening. And so you start having the liquid evaporating, 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 exiting out. Well, you can imagine then that the liquid molecules, the water molecules, they start to recede into smaller and smaller spaces between the spongy mesophyll cell. Doesn't that sound just like what we described in the soil? Pretty much the same idea. If you take what we just talked about in the soil system, soil particles, and replace it pretty much with, instead of soil, it's spongy mesophyll cells or spongy parenchyma cells with water clinging to those. And then as you have evaporation of those molecules, you get the liquid receding into tighter and tighter spaces, which means you generate menisci, plural. The radius gets smaller and smaller and smaller, and you get a tension force built up. And they can actually measure it. The data started to show that very nicely. They had the technology. They can actually show that in the leaf area, in that part of the plant, you have a pretty good tension. Further down in the roots or the base of the stem, the tension's not as good. So you get this tension gradient, right? So it's pretty similar to what we just talked about in the soil system with this tension force. Okay, we have to stop there. We'll continue this on Monday, and then we're also going to stick with the vascular tissue because we also have to think about what's happening with the phloem also next week.